thank you very much for the invitation, and also thank you very much to you, Joaquin and Christian, for putting together what I think is a really great idea for a conference to bring two very interesting communities together that really should have been working on the same problems, but have sort of been working on them independently. So I think this will be a lot of fun to get all these people in the same room and just talking together. So as was mentioned, I'm going to give you guys an introduction here on using electronic coupling to control magnetic properties at the atomic scale. That was what I was originally going to talk about, but the organizers very kindly asked me to extend my talk. So now I'm going to broaden it out a little bit and actually tell you a bit about magnetic atoms and coupling to the local environment. And as Sandra said, if you have questions during the talk, please do raise your hand and let me know. If I don't notice you because I'm just babbling on, just throw something at me or something like that. Just make sure I notice you. Okay, so let's start out by just discussing spins. In the last few decades, there really has been tremendous progress in being able to access single spin systems. So we learn about single spins in classes that we take in school, but what's really amazing is that we can actually go out and probe individual ones. And there are actually a wide variety of experimental techniques that you can use to do this. One of them, for example, is you can use semiconductor quantum dots. Here you can sort of confine either large numbers or even single spins inside little areas of semiconductors. More recently, there's been a large interest in vacancy structures in semiconductors. So for example, NV centers in diamond are currently being looked at because you can access their spins at room temperature. And then of course, there is the main focus of this conference, which is basically magnetic atoms, and I will add magnetic molecules. Sometimes molecules get lost. I sometimes feel bad because, you know, molecules are atoms too, so we shouldn't really forget them. So all of these different systems come into play here when trying to access the physics or chemistry or just general science of spin systems. Now, what's nice about all of these is that in addition to accessing a single spin, you can also access multiple spins coupled together. So you can actually make rather complex 2 or 3 spin quantum dots and use lots of different gates to couple them together. People have now entangled multiple NV centers in diamond as well. And with magnetic atoms and molecules, you can also make various structures that I'll mention sort of later on in the talk, where you can make chains, ladders, you can even grow vertical layers of molecules that are coupled together. So you have the ability to make all sorts of different structures in addition to just looking at one spin sitting on a surface. Now, when you are thinking about spins, most of the time when we draw our little cartoon models, all we think of is an isolated spin floating around in free space. And for many applications, that is really exactly what we want. So for example, if you want to do quantum computing, you really do not want your spin to talk very much with the environment that's around it, and people go to great pains to try to minimize that interaction. So for example, this is a reference to a result that came out a couple of years ago. One of our colleagues at UCL worked with some folks in Canada looking at phosphorus atoms in silicon. The nuclear spin in these systems is actually a very, very good qubit. But because of interactions with various nuclei, you can decrease the spin lifetime, so they actually grew these phosphorus in isotopically pure silicon, right? So this is an extraordinary pain to make this material, but if you do this, you can get lifetimes that are on the order of minutes, right? Close to hours, which is rather phenomenal. So this is very good, but unfortunately, sometimes people get stuck in the idea that this is the only place you want to go, that you actively want to decouple your system as much as you can. And this is the main thing that I would like to convince you is not always true. What I would like you to think about is that there are some situations where coupling to the environment can actually be interesting and in fact even crucial for getting the novel science that you want out of the system. So where might that be the case? Well, I'll tell you a little bit about magnetocrystalline anisotropy, so coupling to the external lattice to get spin stability. We'll talk a little bit about the Kondo effect, where you see the interaction between a magnetic atom and conduction electrons. And then throughout this workshop, I think you're going to see this picture and you're going to hear talks from many people where you look at magnetic atoms on superconductors. And I think this is one of the nicest examples, because this is a situation where if you just look at the superconductor, you have something interesting. If you just look at the magnetic chain, you have something interesting. But when you get the two together, then you really get something very, very different. that wouldn't necessarily have been expected by just looking at the individual components. So that's where I think we should really be going. We should really be looking for these new opportunities in science and in some sense in technology when you understand how the spin couples to its local solid state surroundings. Okay, so this is the general outline for the talk. I'm going to start by looking at an introduction to STM-based spectroscopy, particularly for those of you who do not do scanning tunneling microscopy, which is our probe of choice. We'll just quickly review some of the things you can do with that. We'll then talk about how you can use that to probe magnetocrystalline anisotropy, so that's essentially how the spin interacts with its local crystalline environment. We'll then go on to talk about the main thing that I was going to discuss originally, which is exchange coupling in Kondo. So that is essentially how a single spin interacts with a bath of conduction electrons that are near it. And then finally, I'll tell you how that can also sometimes result in spin coupling, so how you can actually bring multiple spins together to form a more interesting structure. Okay, so let's first start out by talking about an introduction to STM-based spin spectroscopy. So the basic setup for an STM, I'm going to assume most of you are familiar with. You have an atomically sharp tip that is less than about a nanometer away from a surface. You apply a voltage between the tip and the sample, and this is close enough that you can get a quantum mechanical tunneling current going from the tip to the sample. There is an exponential dependence on the tunneling current with the distance between the tip and the sample, and this is what gives us the atomic resolution that allows us to image individual atoms on surfaces. So that's the basic power of the tool. How do we use this to pull out more detailed quantitative information other than just taking pretty pictures? What we do is we think about the tip and the sample as being two Fermi Cs. They're both filled up to a certain energy, which is the Fermi energy, and when you apply a voltage, those two Fermi Cs are offset from each other by V. And then if we think about the current that flows from one side to the other, you can describe it by this fairly simple integral. What you're basically looking at is the density of states times the Fermi function on one side, so if you like how many electrons you have. And then you multiply that by the density of states times 1 minus the Fermi function on the other side, so that's how many holes there are on the other side. So how many of one thing do I have? How much space is there for them on the other side? You integrate up and down, and you get the total current. Now, if you stare at this, what you will realize is that if you take the derivative of the current with respect to voltage, and you make the fairly generous assumption that the density of your states in your tip is flat, then when you look at di dv as a function of voltage, what you will see are features in the local density of states of your sample. And so what we can do with this, therefore, is probe density of states with atomic resolution on surfaces. So how can you use this to study magnetism? Well, here's a nice example from Ali Yazdani's group back in 2006. They were looking at individual manganese atoms in gallium arsenide. And what they were looking for is essentially to try to understand their interactions. And what they do, so if you look at this guy over here, this is a single manganese atom. If they image it at different voltages, they can map out different orbitals. But the more important thing for us right now is looking at this upper left corner. You can see on the left side and the right side two sloping tails. That's basically the band gap of gallium arsenide. And in the center, you see some kind of resonance. That's that peak in red. What's interesting is they developed an atomic manipulation technique that let them build little structures. So here, for example, are two manganese atoms together. And now you can see this density of states feature is split. And that splitting they ascribed to some kind of spin interaction. So what they did is they built a whole bunch of different dimers along different crystallographic directions and with different separations. And then they were able to use fairly general tight binding models to pull out the spin interaction. And you can see the red is the calculation, the blue is the experiment, and they qualitatively agree. So essentially, by measuring the size of the splitting in the density of states, in this case, they were able to extract something about the magnetic interaction that was going on in this system. So this is one way to study these kinds of systems. Now, STM is metal tip looking typically at conducting surfaces, so the standard surface you would think about using is some kind of metal. So the most natural thing you would think about is to put a magnetic atom directly onto a metal surface. This is, in fact, a very good idea. I encourage you guys to do this as often as you can. But what will happen is that the conduction electrons in the metal will strongly interact with the spin. Now, that is actually a very, very interesting thing, but at least initially right now, we're not going to talk about that. What we want to initially do is get all the goodness of the conducting properties of metal in terms of being able to use it for STM imaging, but we don't want this coupling to go on between the spin and the underlying substrate as much as we can avoid. And so the trick we're going to use to get around that is we're going to insert a thin decoupling layer in between the magnetic atom and the metal. So what does thin mean? It typically means it's 1, 2, or 3 atomic layers thin, and that's going to allow you to still get your tunnel current through so you can still have all of your fun with STM. But because that layer is not metallic, it is somehow going to weaken the coupling between the underlying conduction electrons and the spin. Okay. There are a large number of different thin insulators or thin decoupling layers that people use. The one that we have been using for a number of years is copper nitride, so let me quickly tell you about that since I have a feeling you will see this in a couple of talks. So you start with a copper crystal. It basically has a nice square lattice, and then once you have one of these, you will bombard it with nitrogen ions. When you anneal that system to about 300 or 400 degrees C, it will basically order the nitrogens in every other hollow site in the surface, and that will give you a nice island that looks something like this. So this is an STM image of a small copper nitride island on a copper surface. You notice that it looks like a dip in the surface, so it looks like an indentation. The nitrogens and the coppers are actually coplanar, and remember, STM does not give you pure topography. It gives you a mixture of electronic structure and topography. So while this system is actually flat, what this is telling you is that the area with the copper nitride is much less conducting than the copper that's around it. So this is already a good indication that the electronic coupling that we'll get on top of this material is a bit less than it might be on the metal. The other advantage of the copper nitride, which you can just about barely see here, is that there's some kind of periodic structure that's visible. Now, if you can't see it very clearly there, what I can do is basically take a spatial derivative of that to highlight the contrast. Now you very clearly see this very nice periodic structure. Since we know what the lattice looks like, we can use the periodicity to assign the binding sites or the lattice sites. And now what happens is that we have atomic resolution on this system. And that's very nice because when we deposit our magnetic atoms on top of this to study, we know exactly where we're sitting. So what this allows us to do is actually generate atomically precise model systems with magnetic atoms on a substrate. And in particular, we look at manganese, we look at iron, we look at cobalt. People are now looking at nickel and titanium and many other systems as well. And in general, at least on this surface, they tend to have 2 binding sites. They either sit on the copper site or they sit on the nitrogen site. The nitrogen site is metastable, meaning if you apply a small voltage pulse, the atom will hop to a neighboring copper site. So for this talk, I'm going to focus basically on magnetic atoms sitting on the copper sites on this copper nitride structure. Okay. Now, I mentioned before that the most basic spectroscopic technique you can do with STM is this density of state spectroscopy by looking at DIDV. There are a large number of other techniques you can use to extract magnetic information from individual atomic systems. I'm not going to talk about many of these, but these include X-ray techniques. You can also do spin-polarized STM. Those you will see talks from many, many experts at this conference on, so I'm not going to discuss those. The one that I am going to focus on for this talk is inelastic electron tunneling spectroscopy. So the setup for this is more or less exactly the same. You have your tip, you have your sample, you apply a voltage and you measure a current, but now you're going to make an assumption, which is that there's some finite energy excitation for the object contained in your junction. So in this case, it's a magnetic atom, so we might imagine it's a spin excitation. So if that excitation has an energy delta, then you can imagine that your voltage can be applied in 1 or 2 different regimes. It can either be applied such that it's less than delta. In that case, there isn't enough energy for the electron to do anything particularly interesting, so it just tunnels through elastically. Then you essentially have an ohmic junction, DIDV is flat, and so you get a flat line. But if you now apply a voltage that is larger than this energy delta, something new can happen. Now the electron can hop onto this system, donate some energy to create an excitation, and hop off at a lower energy. This is essentially a different path for it to tunnel into the substrate. 2 paths are larger than 1 typically, so if you look at the conductance, it will basically go up at that point. So you will see a step in the IDV, and that step will occur at a voltage that corresponds to the energy of the excitation. Right? This should happen both if the electron goes from the tip to the sample and from the sample to the tip. So you should essentially get a symmetric set of steps in DIDV. And by doing these measurements at finite temperatures, you won't get an infinitely sharp step. It'll actually be smeared out a bit. So as long as the temperature is a bit lower than your delta, you should be fine and you should get these nice smooth steps. So basically what I'm going to show you is a whole bunch of curves where we're looking at exactly this. DIDV is a function of voltage. We're going to look for these steps, and those steps will allow us to extract the energy of the excitations. So if you like, this is exactly analogous to doing something like electron spin resonance, but instead of averaging over millions and billions of identical systems, we can actually do this on an individual atomic spin. Now, particularly for those of you in the quantum magnetism community, I would say don't think of this as electron spin resonance, think of this as neutron scattering, right? And you're going to see that the analogy between inelastic tunneling spectroscopy and neutron scattering is actually much more precise than that. But essentially, this is neutron scattering where you don't get wave vector resolution, but you do get spatial resolution, right? And that makes sense because we're looking at a finite system, so there probably isn't a wave vector dependence in a single atom, but there is spatial resolution for this thing. So keep that in mind as we go through this. Yes?
A little bit analogous to NMR.
Yeah. I mean, all of these things are more or less probing it in similar ways. Yeah, so that's the basic idea here. Now, this, if you like, is analogous to continuous wave ESR. There are analogies to pulsed ESR that you're going to see in other talks as well. So people can now use similar kinds of techniques to do coherent measurements of lifetimes and even do manipulations eventually. But for now, we're just doing the continuous wave version. Okay, so that's the nice introduction to STM spectroscopy. Now let's go actually apply this to learn something about our spin system. So we're going to start with a fairly, yeah. Yes, I will do that later when I get to the end of this section so you can see that, okay? So let's start with a simple system. We're going to look at an iron atom sitting on a copper site on this copper nitride. So I don't have an image of it for you here, but I'll show you some images later. Essentially what we measure is dI/dV as a function of voltage, and the first thing I want you to keep in mind is that the voltage scale here is relatively small. This is plus or minus 10 millivolts, so we're looking at relatively low energy excitations. These measurements were done at the IBM group in San Jose. This was done at about 0.5 Kelvin and in the absence of a magnetic field. And what you can see in dI/dV is it looks more or less symmetric around the Fermi energy, so positive and negative are more or less the same. And what you clearly see are steps in dI/dV. And there are 3 different steps. One of them occurs at fairly low energy, about 0.2 millivolts. And then there are 2 steps at higher energy of about 4 and 6 millivolts. Now, the first question you might ask is, why do we see any steps at all? If these things are spin excitations, why is it that we see something in the absence of a magnetic field? So if you think about a spin as a little arrow floating around in free space, which many of our little models would suggest it is, then this doesn't make any sense because in free space, all the directions are the same, and there shouldn't be a difference between the different orientations, so there can't be an energy difference either. That is absolutely true, but it's not what we have. What we have is actually a spin on a surface. And once you have something that breaks the rotational degeneracy, then the different orientations are allowed to have different energies, and once they can have different energies, then in principle you can measure that. So these measurements that we're doing are actually extracting the difference in the different spin orientation energies for our system. How do we model this more quantitatively? Well, we use a fairly straightforward Hamiltonian to do this. These are the set of spin Hamiltonians that people use for a variety of different systems. In this case, there are going to be 3 terms. The first term is the Zeeman energy that you all know and love. And then the second 2 terms are the anisotropy terms. The first one is dsc squared. So sc, remember, is the projection of the spin along some axis. So this is basically measuring how far the spin wants to be from a particular axis. So this is what's called axial anisotropy, and it breaks the degeneracy into various z levels. And then there's a third term, which is the transverse anisotropy, which is basically a term that then mixes these states that were non-degenerate over here. So these 3 different terms are the ones that can come in when you're looking for anisotropy for individual atoms on surfaces. So how do we figure out what this anisotropy is? Well, we play a cute little trick. We apply a magnetic field in the plane of our system. In this case, we orient the magnetic field along the nitrogen rows, and that's particularly nice because if you look at this iron atom over here on the left, you can see that there's a nitrogen on the left and the right of it. But if you look at the iron on the right, you can see there's a nitrogen above and below it. So in the case on the left, the magnetic field is oriented parallel to the nitrogen axis of that atom, whereas if you look at the case on the right, the magnetic field is oriented perpendicular to that. So by applying the same magnetic field but choosing different atomic sites, we effectively get 2 different orientations of magnetic field. So what we see here is that as you increase the magnetic field, those excitations that we saw at 0 field change. So if you look at the case on the left, both of them go up in energy. If you look at the case on the right, the highest energy one goes down. So not only does the excitation energy change, but the way it changes depending on which direction you apply the field. So it's not just the magnitude of the field that matters, it's the direction that matters as well, and that is pretty much the definition of magnetic anisotropy. Each direction is sort of different. So we already know that there is some magnetic anisotropy here. Same thing for the lowest energy excitation, you see something different. Now what we can do is we can look at the energy as a function of magnetic field. We can try to measure these various parameters from our spin Hamiltonian. Just from zero magnetic field, in this case, we can extract the anisotropy parameters. So this is D equals minus 1.5 millivolts and E equals 0.3 millivolts. And indeed, we can then turn on the magnetic field and see how well they agree. And you can see there's excellent agreement that we get, not just in the magnitude, but in the different directions, just by determining these simple parameters. So what's nice about this is that it allows us to actually measure the magnetic anisotropy, not for a bulk system, but literally for a single atom sitting on a certain location on a surface. Now what's nice about this is that there's actually a lot more information in this spectrum than just the energies. Right? So you get the energies by diagonalizing a simple Hamiltonian like this. Here are the energies you would get by doing that. You notice this is a spin 2 system, so there are actually 5 different levels. Transitions, of course, go between levels, so there should be 4 different transitions. But we can try to learn more about this system by looking at the results of this diagonalization. And whenever you diagonalize something, you don't just get a set of eigenvalues, you get a set of eigenvectors as well. Right? So these are the eigenvectors that correspond to the eigenvalues over here. So let's stare at this a little more closely. So you notice this is a spin 2 system. I told you that D was negative. Negative D means that you favor the high spin states and you disfavor the low spin states. So you can see here the ground state wave function is made up of mostly spin plus and spin minus 2, and then there's a little bit of spin 0 mixed in there as well. The first excited state is also spin plus or minus 2. The second and third are plus or minus 1. And then the highest state is actually mostly spin 0, but it's got a little bit of spin plus and minus 2 mixed in. Why is this important and interesting? Well, let's look at how you would make transitions from one state to the other. If you wanted to go from the ground state to the first excited state, there's a large component of overlap between the plus and minus 2 states. That's a delta M equals 0 transition. That seems pretty reasonable. If we want to go to the second and third excited states, those are mostly spin plus or minus 1. So then we would need a delta M equals plus or minus 1 transition. That sounds pretty reasonable as well. And then the third transition would be to a state where there's mostly spin 0. And then there's really not going to be very much overlap. The thing we would really like to do to connect these is a delta M equals 2 transition. That doesn't seem very likely if we have a single electron doing this. So probably it's going to be a delta M equals 0 transition, and then there's just not going to be very much overlap over here. And indeed, just from that qualitative picture, you can see that you would expect these 3 excitations to be strong and the fourth one to be very weak. And in fact, that's exactly what we see. We do not see those higher energy, this highest energy excitation very strongly normally. Now we can go one step further than that. We can try to quantify this by measuring the relative height of these steps. So we'll call this I1, we'll call this I2, we'll call this I3. And then because we don't know the overall amplitude, we'll just normalize by the sum of these guys. So we can plot this as a function of magnetic field. You see very clearly that the first transition gets very, very weak very quickly with magnetic field. The second one gets a little bit stronger, and the third one gets a little bit weaker. So how can we try to understand where this comes from? Well, we can basically use a simple Fermi's golden rule approach to try to model this. And in Fermi's golden rule, what you basically say is the transition rate is some kind of matrix element between the initial state and the final state with some kind of operator that couples them, and then you square that. So if we're dealing with spin states, then it's natural to expect that our spin operators are going to be the thing that couples us. We didn't see any reason to think that x would be any different than y would be any different than z, so we basically just took projections of all 3 of these and added them up. This was a total guess. Here you can see the calculated intensities. When we diagonalize our little Hamiltonian, you get the eigenvalues and the eigenvectors, so all you have to do is plot this and you get your answer. So this is the measurement and that is the calculation. Right? So this is based on the eigenvalues that we extracted from the measurements, and you can see that the agreement is really very, very good. So that's really great. We know how to model the IETS line shape, so we can actually generate simulated spectra, and now, lo and behold, we can get very, very good agreement between what we think we would get and what we actually find when we're doing these kind of inelastic tunneling measurements. Right? Now, why do we use this? Where did it come from? Well, initially it was just a guess, but as it turns out, this is exactly the same matrix element you get for neutron scattering, and there's a reason for that. This is basically just exchange coupling between our tunneling electron spin and our atomic spin. And so whenever you have some kind of scalar exchange coupling, this is just pretty much what you're going to get in this situation. Now, this is written as sx squared, sy squared, sz squared. If I write this out in a slightly different way and I replace sx and sy with s plus and s minus, then you can also very quickly see what our selection rules are going to be, right? We're going to have delta m equals 0 and delta m equals plus or minus 1 selection rules. Okay, so we were very proud of this when we first did this. This looks very, very good, but as it turns out, this is not the full story. If you stare at this very closely, you will notice, for example, that the calculation predicts that the intensity of the step should be the same at positive or negative voltage, but in the experiment that is definitely not the case. If you look at the step shape, it should be nice and flat, but in fact it actually experimentally looks like a peak. There is no way you're going to get that from this formalism. Luckily, people that are smarter than us figured this out. So in the next talk, there were a number of people who have worked on this. The most recent one, and I think the canonical work on this now, is going to be Marcus's beautiful paper in New Journal of Physics. I would strongly encourage all of you to go download this and read it. It's only 50 pages, and it's pretty much everything you ever wanted to know about this. The essential result is some kind of scattering with the surface. So again, coupling to the surface becomes important. Marcus will tell you all about that. All I will show you is that the agreement is pretty damn amazing. Right? So now you get really good agreement between all of the features that we didn't understand before and we do understand right now. So I'm looking forward to seeing that in the next talk. So that's basically how we can extract magnetic anisotropy. Now let's go on to talk about what I was most interested in talking about, which is basically exchange coupling between this magnetic atom and the substrate. Okay. So I had mentioned before that when you put a magnetic atom on a metal surface, the conduction electrons in the metal will tend to try to screen this magnetic spin. The experiments that were done to show this date back to the 1930s, but on a single spin, this was first done in the late 1990s by MAQM's group. Actually, no, with a single atomic spin, it was first done in MAQM's group with cobalt on gold. I had mentioned earlier that there are other systems for looking at single spins. One of the amazing coincidences is that in quantum dots, this Kondo effect was also seen in exactly the same year, in 1998. Right? So you can see there are many analogies between what you can do with all of the different kinds of spin systems. So what did they do here? They deposited individual cobalt atoms on a gold surface. Each of these little circles is a single cobalt atom. They then went off and did standard density of state spectroscopy measurements. So if you measure dI/dV versus voltage, now notice that this is a much larger energy scale. This is plus or minus 100 millivolts. If they just did the spectroscopy on the bare gold, they saw more or less nothing. You see dI/dV is flat. But if you look on the cobalt atoms, you see this large resonance around the Fermi energy, and that is an indication that this interesting feature, which is the Kondo effect, is going on. So what happens in the Kondo effect, for those of you who, I think most of you are probably familiar with it, but just in case, what's going on here is we are coupling an atomic spin to a bath of conduction electrons. You can model the conduction electrons as a nice Fermi C over here, and then you can, in the simplest model, think of a single orbital that is weakly coupled to this Fermi C. This is the Anderson model picture of this. And what happens is you have a single spin sitting over here, and if you want to add a second electron to this system, you need to pay a charging energy U to go up here. Right? So in its default state, this will be singly occupied. It will have a net spin. As you turn on coupling between the bath and this single spin, electrons can hop on and off, so they can more or less scatter with this. But if you go below a certain energy, something very interesting will happen, or if you go below a certain characteristic energy scale and temperature. Basically, this hopping on and off will actually form a many-body macroscopic quantum ground state, and it will create a singlet. Now, what's essentially going on is you have hopping on and off of this atomic site, and the hopping is such that you actually flip the spin every time you do it. Since this has to cost no energy, what it means is that you need to take an electron out of the metal with a certain spin and put it back in with the opposite spin, which means you need filled states and empty states with opposite spin orientations at the same energy. There's pretty much one place where that happens. That's at the Fermi energy. You'll essentially see an enhancement in scattering at that energy, and so the characteristic signature for this is actually a peak in the density of states that appears at the Fermi energy. So this is what we often look for experimentally. We look for these peaks in the density of states at the Fermi energy to try to figure out when this Kondo effect is going on. So before I've showed you iron on copper nitride, now let's switch to looking at cobalt on copper nitride. Cobalt has one more electron in its D shell, so it should be a spin 3/2 system rather than a spin 2 system. Here's a very pretty picture of one of these. You can see each of these little bumps on here is taken for a single cobalt atom, and each of these little squares is our little copper nitride. And we can now do spectroscopy on this, again, DI/DV between plus and minus 10 millivolts, so we're back on the low energy scale. And now you notice two things in our spectrum. In addition to this nice little peak in the density of states, which I'm going to tell you is a Kondo resonance, you also see these steps at positive and negative voltage, which hopefully you now believe me are these inelastic tunneling features. So what you can see here is that we now get a Kondo feature in addition to getting the inelastic tunneling. Right? So we can do the same thing we did before for the iron. We measure the energy of these features as a function of magnetic field. Again, you can see that the central peak splits at different rates depending on the orientation. So these are two different orientations of the magnetic field. The steps also shift in different rates. We can use that to extract the anisotropy parameters. In this case, the main take-home point is that the anisotropy is now positive rather than negative. So we have a positive D term rather than a negative D term. And what that means is that if you start out with a spin 3/2 manifold, you don't favor the high spin states, you actually favor the low spin states. Because this is a half integer spin, you are Kramer's protected, so you always have a doublet in your ground state. And so therefore, when you're looking at low energies, you will get Kondo screening. But if you excite to higher energies, you can excite out of the ground state doublet up to the first excited state and measure the energy of that spin excitation. So what you see here is that Kondo screening and anisotropy can coexist in one of these systems. Okay, so that's the basics of what we can do. We can look at Kondo screening and we can look at anisotropy. What we then wanted to do was explore how this might vary and how we might be able to tune it. And this is one of the real powers of the scanning tunneling microscope. If you're looking at a bulk averaging technique, you're going to average over this entire region and get everything you can from this area. But with the STM, you can literally look at this atom or this atom or this atom and see how they're different and see how the local environment can affect it. And so in particular, what we wanted to do was take these cobalt atoms and move them towards the edges of the copper nitride island to see how their structures changed when they moved towards the edge. So we did this with these small copper nitride islands that I'm showing you on the left. That was very interesting, and we are still in the process of trying to understand that, so I'm not going to tell you in detail what's going on with those. Instead, I'm actually going to focus on what happens when you look at much larger copper nitride islands, which occur when you basically saturate the entire surface. So here what you do is you just put a lot more nitrogen into the surface, you cover the entire surface with copper nitride, and then you get much larger islands, which can be as large as about 20 nanometers by 20 nanometers. So now let's focus on that, and let's see what happens as we move one of these cobalt atoms from the edge of this copper nitride to the center. So first we'll start with this atom over here, that's the one on the top. Again, we're going to do DI/DV as a function of voltage between plus and minus 15 millivolts. For this cobalt atom on the edge of a large copper nitride island, again, we see a peak at zero bias, and we see these steps at about 5 millivolts. So this looks more or less the same as what you saw before. But now, if I move from the edge atom to a little bit closer to the center, you notice that the signature has changed. The Kondo peak has gotten weaker, the inelastic tunneling step has moved to slightly higher energy, so something is now different. And by the time you get to the center, the spectrum looks very, very different. The peak is now completely gone, meaning we've more or less suppressed the Kondo screening. But the inelastic tunneling feature, which is the spin excitation, has almost doubled in energy. And this is rather phenomenal, right? Remember, I told you that this island is about 20 nanometers across. So just by going about 10 nanometers from one edge to the center, we have completely removed Kondo screening and doubled the energy of the spin excitation, right? So very, very dramatic changes just by going from one point to the other. So what could be going on? How would this be happening? Well, we know that the anisotropy is changing. So the first question might be, is the local crystal structure changing? So the good thing about STM is you can actually measure lattice constants if you have atomic resolution. So we did this, and at least as far as we could tell, up to a few picometers, which is our resolution, we did not see any change in the lattice constant across the island. Now you can do a more sensitive test, which is this copper nitride, if you look at the spectroscopy measurements that others have done, actually has an onset in density of states at about 2 volts, which is roughly comparable to a band gap for a semiconductor. And you can follow that edge as a function of position. So the black one is at the edge and the red one is at the center. And you can see that as you go from the edge of the island to the center, this band edge shifts by about, let's say, 0.1 volts, right? Now, 0.1 volts out of 2 volts is about 5%. So by going from the edge to the center, the gap changes by about 5%. For most semiconductors, the gap is very, very sensitive to the lattice constant. So if this is changing by 5%, the lattice constant is probably changing by much, much less than 5%. So what does that mean? It probably means there's a tiny change in the lattice constant from the edge to the center. That probably will play some tiny role in what we're seeing, but it certainly will not double the energy of the excitation. So something different has to be going on here. And what we think is going on that's different is the exchange coupling is changing. So this Kondo screening is caused by exchange scattering between the impurity spin and the conduction electrons in the metal below. That's going to be through some kind of tunneling or hopping process. That will be very, very sensitive to small changes in the lattice constant and therefore may change as you go from one side to the other. Now, notice that the band gap actually gets bigger as we go from the edge to the center. If the gap gets bigger, you would naturally expect the exchange to go down. And indeed, that's exactly what we see. This Kondo peak should be some kind of measure of the strength of the exchange coupling. And indeed, it does go down as we go from the edge to the center. So there's good reason to believe that the exchange coupling at the edge is much, much stronger than the exchange coupling at the center. So both of these little experimental signatures support that. So now the question is, if the exchange coupling is changing, what effect does that have on the spin excitation spectrum? And in order to understand that, we went out and reached for help from our very nice theory colleagues. So we first called Joaquin. Joaquin basically did a nice perturbation calculation with Fernando and got a very nice answer that I was very, very satisfied with and really was very happy to go forward with, but they were not happy with it because perturbation theory does not give you a Kondo feature. And so then we reached out to our colleague David Jakob, who did a very nice multi-orbital Anderson model of this to really give us the correct answer. So how does this work? Well, they're both correct. I shouldn't say that. But to really give us the full spectrum of the picture. So what is going on here? We're basically doing the simple Anderson model that I described before, but instead of having a single orbital, we now need multiple orbitals to incorporate the 7 electrons that are going to go in there to give us a spin 3/2 system. We're going to solve this in the one crossing approximation, and I'm very happy to be able to say that if you want to know what this is, you have David in the audience who can tell you the answer to that. It's basically some kind of approximation for some of the diagrams in this thing. And then what we do is we solve this, and we begin with a set of discrete levels that are coupled to our reservoir. So we basically model the reservoir levels, the impurity levels, and then we turn on some kind of hopping between the reservoir and the atom. So basically, we allow charge fluctuations to go from the isolated atom into or out of it. We pay a charging energy if we add or if we remove something. And from this, we can basically recreate the Coulomb interactions, or we can recreate the Kondo interactions that lead to the screening of this spin. What do we get from this kind of calculation? The most straightforward thing we get is the spectral function, which is effectively like the density of excitations in our system as a function of energy. So I can plot that for you over here. So notice that we're starting out with a reservoir of electrons. If there's no coupling, you can think of these orbitals over here and over here as being infinitely sharp. But once we turn on our coupling, they will be broadened by an amount gamma. And that gamma is actually what's going to measure our coupling here. If we look closer at the Fermi energy, what you can see is something else as well. First of all, you can see a peak in the density of states at the Fermi energy. That's an indication that we now have our Kondo screening going on. But then at slightly higher energies, you can also notice these steps, which are an indication of our spin excitations. Right? So from this spectral function, we can extract both the energy of the spin excitation and the fact that we have some kind of Kondo screening. So now that we have this, all we have to do to basically understand the impact of the exchange coupling is change the exchange coupling, which basically means we vary gamma and see what happens. So what happens when we have small gamma? That's basically this. You see these peaks are relatively narrow. If we increase gamma and we look at a higher energy scale, you look at these guys and you see they're now much, much broader, which is an indication that the interaction is much bigger. And more importantly, if you look at lower energy features around the Fermi energy, you see that our two features have changed. First of all, that peak has gotten much, much bigger. So we've increased the exchange coupling, which means we've increased the strength of our Kondo interaction. That's perfectly sensible. But the more surprising thing in some sense is that we have also shifted the position of our spin excitation. Right? So notice that in the small gamma limit, this guy was more or less up here, and it was more or less at the bare energy of the spin excitation. But now it actually occurs at a much lower energy. So just by changing gamma, we can change the energy of our spin excitation. Right? Now, in this case, we were changing gamma, which is this broadening term over here. If you change the energy of the orbitals or you change the charging energy, all of those things go into determining this, so any of them will actually have the same impact. In our case, we think that we're changing gamma, but more or less all of them would do the same things if you had those realizations in your system. So these are the experimental spectra that we had. These are some calculations that we did, and you can see that the qualitative trends are certainly very, very well agreed with each other. So this is pretty much what we think is going on. Now, I will point out that in this case, we do not actually know what our gamma values are because we had no direct way of measuring that, and I'll get back to that in a second. So what you can basically see here is that as you change gamma, the energy of the spin excitation is changing. Right? So you start out with something at relatively high energy where there's no gamma, and as you increase gamma, which is marked by the Kondo feature, then you can basically shift this step to a much, much lower energy. And as Joaquin likes to point out, I think we are particularly proud of this because I think this is the first time that Kondo has actually been used for something useful. Right? We have actually used Kondo as a measure of the exchange coupling. Right? So remember that. You've actually seen something useful for Kondo here today. So why is this particularly interesting? Well, it's interesting because before what I told you is that this magnetocrystalline anisotropy was more or less the crystal structure around the system. Right? It's basically where are your little point charges sitting around your spin. What's amazing here is that these D and E terms, which I told you were the things that describe this, don't just depend on the crystal, they actually depend on electronic properties. They actually depend on exchange coupling, they depend on Coulomb energy, they depend on the energy of the orbitals. So what that means is you can actually use an electronic knob, which is the exchange coupling, to tune what you normally think of as a structural property. So that's really neat because this gives us a completely new knob for tuning the anisotropy in our system. Right. Now, what's going on here? What's going on is that we're basically coupling an open quantum system to some kind of reservoir. And all of you know from your undergraduate physics classes that if you couple a quantum system to a reservoir, you will get some kind of energy level shift and you will get a change in lifetime. Right? This is basic perturbation theory that tells you that. Now, this is so common in particular that lifetime changes are so common that you can even do medicine with it. Right? This is how an MRI works. You're basically measuring changes in spin lifetimes as a function of position. And this is the thing that allows us to tell that we actually have brains inside ourselves without cutting ourselves open to check. But actually measuring energy level shifts is not so common. Why is that? Well, in an uncoupled case, the lifetimes are infinite, and the coupled case, they're finite. So measuring not infinite is straightforward. But actually trying to measure energy shifts is very hard because spectroscopically you never measure the bare energy, right? A spectroscopic measurement is always going to be the renormalized energy. So if you're just doing a single measurement, the only way to really extract the bare energy is to do some kind of idealized calculation, which in some cases like the hydrogen atom you can do, but in most cases you can't. So what's nice in our situation is not that we can somehow magically extract the bare energy, but that we can tune the exchange coupling, so therefore we can vary the strength of that exchange interaction. And by tuning it, we can basically see what the impact is on our actual renormalized spectrum. Okay. And it's one of the few situations where you can actually easily do that for this. Now, one of the things I pointed out is that we only had qualitative agreement because we could not figure out exactly what gamma values. Once again, if you want to get this right, you go to Marcus, and Marcus tells you what the real answer is. I gave you the little hint already, which is that the line shape of this inelastic tunneling spectrum is somehow related to the coupling to the surface. And if you figure out how that works, you can actually quantify the strength of the exchange coupling. Marcus may tell you a little bit more about that. There's a paper on the archive that describes that. A similar feature has also been seen for the normalization of the G factor, which is more or less analogous to the night shift that people see in NMR. So you can see this renormalization is actually popping up now in more and more places. And in fact, if you look at older calculations, you can sometimes see hints of it as well. So it's a fairly general phenomenon. And in fact, Joaquin, Fernando, and I have written a nice little surface science article that sort of tries to put all of this in perspective, how a simple perturbation calculation, well, it's not simple, I can't do it, but they can do it. But a straightforward perturbation theory calculation can give you insights onto this in many different manifestations that may pop up in many, many different areas. Okay, so with the remaining time that I have left, I thought I would move from that and now go on to spin-coupled systems. So up till now, we've been talking about individual spins interacting with their local environment. That is genuinely a lot of fun, but at some point you get a little bored and you want to do something a little more than a single spin. So how can you do this? Well, the simplest way is to do something like this. You basically deposit a bunch of atoms, see what you get, and hope for the best. You can imagine that those of people who are control freaks don't really like this because they really want to make exactly the thing they want. And for those people, we've developed a technique where this does work. So what you can do in some situations is you can do manipulation with your STM tip. So here what you do, in this case for atoms on copper nitride, you push the tip into the surface, you apply a voltage pulse, and if everything works nicely, the atom hops onto your tip. So you can see we did it over this atom, we picked it up, and then you reverse this process in another location, you push the tip into the surface, you apply another voltage pulse, and then drop the atom off, and then there you go. Now you can see in PowerPoint this looks very nice and easy. In real life, it's not quite that easy, though when you get good at it, you can actually do this quite often. And I think you'll see in a number of other talks that you can actually build rather amazing structures this way. What we did when we initially figured this out is we started by building a dimer, and then we built a chain of these guys up to 10 atoms long. And the nice thing is that each of these guys is a single manganese atom sitting on a copper site with two neighboring nitrogen sites, with another manganese atom on a copper site next to it with a nitrogen site. So this is an atomically precise chain of 10 magnetic atoms built one atom at a time. And what's doubly nice about this is that not only can you build these, but you can do spectroscopy on it as you build it. So here now you see the spectrum of this chain for 1, 2, 3, all the way up to 6. And what you can see is that each spectrum is different. So just adding one more spin onto this thing completely changes the excitation spectrum. How do we model this? You already saw the answer. You basically just use some kind of simple Heisenberg coupling. For a dimer, the Heisenberg coupling is completely independent of the magnitude of the spin, but it will directly give you the J coupling. So we can extract from this a coupling strength of about 6 millivolts, which is really quite strong. From the trimer, the spin does make a difference in what you get. So if you have a spin 2, then it'll be down here. If you have spin 5 halves, no, if you have 3 halves, it'll be down here, and spin, well, all right. So if it's 3, it's going to be up there. So the different spin values will give you different excitation energies. You can see 5 halves, which is what you would expect for the free spin of the manganese atom, agrees best. So just from that, we now have all the different terms in our Heisenberg model. And now as long as you have a computer that's big enough to hold these matrices in it, you can diagonalize it and outpop the excitation energies, and you can see that they agree very, very well. So what we've been able to do here is build a chain of Heisenberg-coupled atoms that go one atom at a time, and we can follow the evolution of this excitation spectrum. Now, it is almost certainly the case that S.S does not fully encapsulate everything that's going on here. For record purposes, we did this in 2006, which is actually before we learned about anisotropy. So we did not include anisotropy in the calculations. There is almost certainly anisotropy in here, so you could include that. There could well be non-collinear terms in here as well, but to zeroth order, this exchange coupling does an excellent job of describing a lot of what's going on in this system. Now, yes? Yeah, okay, so that's actually an inelastic tunneling feature. So this manganese atom has anisotropy. It's a very, very small anisotropy. So that's, if you did this at 0 temperature, it would be a nice little sharp step, but it's actually smeared out. So I could show you the excitation spectrum for a single atom, and you would see that evolve very nicely. But actually, that very nicely lets you see that this has a spin of 5 halves. There's no bump at 0 bias, so this has spin 0. This has a spin 5 halves 0. So you can see this sort of spin, no spin coupling that would be natural for an antiferromagnetic coupling in this case. Okay. So what is actually going on here? What are we actually building? So this is a DFT calculation for the copper nitride. I'm not going to go into the details of this at all. What I'm going to very quickly show you is that you have nice uniform electronic states in the metal, but the electronic states are actually fairly strongly coupled in the top surface, so they look like they're forming a sort of molecular layer on top. If we put a single manganese atom in, the nitrogen atoms come out and cradle the manganese. If you put two manganese atoms in, the central nitrogen atom comes up and actually forms a little bridge. So what we think is going on here is that these manganese atoms are coupled through superexchange. So what's neat about this is that if you just look at the images, you might think that you're making a manganese chain. You're not. What you're really doing is you're making a manganese nitrogen chain. And the reason I like to say this is that this thing actually then is analogous to one of these things. So you see my friend the molecule has come back now, right? So it turns out that molecules aren't atoms too, atoms are molecules too, right? And what we're basically doing is building a single molecule magnet, but instead of using various chemical techniques to do it, we're doing surface manipulation to make it. So this is a molecular magnet that's basically built in the surface of a material. And we're cheating, we're using the nitrogen atoms that are in there to act as our exchange bridges. In most molecular magnets, it's usually oxygen, but it's more or less the same idea. Okay, and then finally, I think I have about 1 minute left, right? Something like that?
Yeah, sure.
Okay. Let me tell you about another set of little interesting pairs that I have more time. All right, excellent. So let me tell you about a pair of atoms that we built. So this was in 2009. Again, you notice there's a name that's showing up here fairly frequently. This is an iron atom and a cobalt atom. So this is a pair of atoms that are now not the same but are different, and they're no longer spaced in adjacent copper sites. They're separated by two hollow sites. Indeed, the STM image already tells you something is different because now you can actually see the two atoms separately. Why is that interesting? So here is what you would expect if you just looked at an isolated cobalt atom and an isolated iron atom. These are the spectra we've seen up till now. When you put the two of them close to each other, however, you see the spectrum changes quite a bit. They're not unidentifiable. You can see this clearly looks similar to an iron spectrum, and this clearly looks similar to a cobalt spectrum, but something has definitely changed. So what has changed is that something is allowing them to talk to each other. The interesting thing here in some sense is also that you notice that even though these two spins are now clearly coupled together, one of them shows Kondo screening while the other one doesn't, which I think is quite neat and is something that should be thought about a little bit as well. So how do we understand this? It's actually fairly straightforward. You basically just use all the terms that we've talked about, so the magnetic field, the anisotropy terms, and then you just add an exchange coupling between these two guys. That's pretty much it. And I won't bore you with the details, but essentially, if you look at the energy of these excitations as a function of magnetic field, you can see the solid big dots are where we measure excitations in red for the cobalt and in blue for the iron. The lines are basically calculations we did using that Hamiltonian on the previous slide, and you can see that they agree very, very well. And we're using here a J of about 0.1 millivolts. So notice that the J is about an order of magnitude smaller than the anisotropies we're using. So why do I point this out? Well, in some sense, this is more or less the same thing as the manganese chain, but there are a couple of important differences that I want to highlight here. Number one, what I think is very, very interesting here is that you see the red dots and the blue dots are not in the same place. What does that mean? That means that the excitations we see on the iron atom are completely different than the excitations that we see on the cobalt atom. And the reason for that is that what we're doing here is we're not exciting both spins simultaneously. We're literally exciting a single spin in this pair. And what that allows us to do is probe different excitation spectrums. And indeed, the color in these lines is basically the intensity of the excitation that you would expect to see using that matrix element that I showed you before, but only flipping one of the two spins. So what we're doing here, for example, with the cobalt is we're taking the ground state of this system, we're flipping the cobalt spin, so we're applying the SC operator here, and then we're projecting that onto the set of excited states. So what you can do is you can actually probe different excitations at different parts of the chain. And I think that's important to realize, that not only do we have a spin that has a finite number of elements, but we can actually probe different parts of the spectrum along different points of the chain using this kind of technique. Right? And then the second thing is that these guys are actually distinct. Right? You can actually do this kind of thing, and you can see that you get different spectra than you would for just a simple chain, where it's just one spin that's all the same. Okay, very good. So this is more or less the end, though I want to add one or two quick comments. So what I hope you've seen here is that magnetic systems are very, very interesting to look at the atomic scale, and in particular that STM is a powerful tool for constructing model quantum magnets, in particular of finite size. And I think this is one of the very, very interesting advantages that we have here. In many, many quantum magnetic systems that are in bulk, you typically assume that they're infinite. Here we can actually look at finite-sized magnets. And why is that nice? It's nice not just from a simple computational perspective that it's easier to calculate 6 than infinite, but you actually will get different physics when you have smaller systems. So I think it's worth thinking about how those would be different. I've shown you that you can use STM-based spectroscopy to probe magnetic interactions with atomic resolution, and in particular, that not only can you see where the atoms are, but you can actually excite individual atoms in a particular coupled system, and that might let you extract things, so for example, like edge states, which you'll hear spoken about. And then finally, the big picture that I hope I've convinced you of is that the coupling to the local environment, be that the crystal environment or the electronic environment, is not a bad thing, and in fact it can be a very, very good thing. And it can yield interesting quantum phenomena that we should be thinking about exploring in more detail. So that's a lot of what I'm going to tell you about. I just wanted to highlight a lot of the different things that you're going to see at this conference, so you can see that this technique has been used to do a huge number of really, really beautiful things. What has been going on in the field? Well, the most straightforward thing you can imagine is that people are just building different kinds of model quantum magnets. So people have built spin ladders. You can start to build things like Kagome lattice elements. So you can really do a lot of different things just by putting these different spins in different locations, and you can get a whole bunch of different kinds of couplings. All of these guys assume antiferromagnetic coupling. Getting ferromagnetic coupling is much harder, but it can be done. So Xander's group last year reported a ferromagnetically coupled spin chain, so that now opens up ferromagnetic interactions. And then in the Wiesendanger group, they've been looking a lot at non-collinear interactions. This is going to be hugely important for some reason. That is very, very interesting, right? Now you get more interesting topological interactions that come into play. So I think these kind of interactions are going to become more and more exciting, and a lot more people are going to start thinking about how they can implement them. In addition to just different kinds of models, people are also building on multiple surfaces. So you've already seen what happens when you put these magnetic atoms on metals. You can get Kondo interactions, but you can also get much stronger interactions with the surface. So for example, you can induce large spin polarization in the metal, and indeed more recently, the Wiesendanger group is going to report an interesting interaction that happens when you have multiple orbitals that are involved and not just a single orbital as you do with simple Kondo. Really exciting stuff that is coming out. People are now also looking at these magnetic atoms on various 2D materials. So we've already seen copper nitride, which indeed is a 2D material, but people are also looking at boron nitride and graphene and lots of other thin insulating or thin metallic or thin whatever layers. People are also now looking at more interesting surfaces. So like for example, our group is now looking at magnetic interactions on silicene. And 2D materials are particularly interesting because you can get different kinds of exchange couplings between different materials that potentially could have much longer range. People are also looking at magnetic interactions on topological insulators. And then finally, as has been mentioned a couple of times, you can now imagine doing this on superconductors. People have been looking at the interface between magnetism and superconductivity for a couple of decades, but what has now been realized is that if you throw in topological order, you can get much more interesting quantum states. So with that, I would like to sort of almost end with a big question, which is basically one of the things I would love to get out of this workshop is a set of questions and not a set of answers. So I think we've spent a couple of decades developing these kind of techniques to build these kind of systems. I think it would be great if we could now come up with a set of questions that we would really like to address, right? To really have some kind of major milestones for the community to push forward to. What would we really like to see? Maybe that's fractionalization, maybe that's looking for these topological states, but just what kind of ideas are there, not just for coupled systems, but also for, let's say, spin liquid systems? What kind of things can we do when we can build things one atom at a time? And then finally, I want to do one more quick little thing, which is to say molecules are atoms too. I think it's a shame not to mention this. So we've been doing a lot of work on molecular systems. So here is an iron thiocyanine molecule. You can see that it is actually not a big messy chemistry thing. It is actually just a bunch of little atoms behaving nicely together. In this case, we also found coupling to the environment was important. We saw a feature that shifts by about 100 millivolts in a 6 Tesla field, so about 100 times larger than the Zeeman energy. You can read more about that in this article over here. We're also exploring more complex interactions. So if you take 2 of these thiocyanines and sandwich an F-shell atom in the middle, you get F-shell magnetism. You can then study charge transport through this and how that charge transport is modified by the coupling to the surface. If you're interested in that, my former PhD student and now postdoc Ben Warner, who's in the audience, has a nice little poster about that, so please go bother him about that. And then finally, the most important thing, let me acknowledge all the wonderful people that I've had a chance to work with. A lot of the work that I showed you was done at IBM, so that group was started by Don Eigler, is currently run by Andreas Heinrich. I had the pleasure of working with a lot of these folks, either while I was there or afterwards. And we had a number of visitors as well. So it was really a very dynamic and exciting time to be there. And then the exchange coupling work, I particularly want to acknowledge my PhD student, Jenny Oberg, my postdoc, Reyes Calvo. We had an excellent theory collaboration with Joaquin and Fernando and David at the Max Planck. And then we did some supporting measurements in Spain at the LMA in Zaragoza in David Zerate's group. Funding for this comes from the Engineering and Physical Sciences Research Council in the UK and the government of Spain. And with that, I would like to thank you very much for your attention.